In this video, I'm going to show you how to compute the volume of solids with right triangular bases and cross-sections perpendicular to the x-axis. So here let's start off with an example. Compute the volume of the solid which has a triangular base bound by the x and y axes and the line y equals 1 minus x, and whose cross-sections are squares. So here we've got a little graph of the situation. We've got the line y equals 1 minus x that's plotted there, and then the region is also bound by the x and y axes, so we want to shade in everything that's bound in the first quadrant by the x and y axes and beneath the line y equals 1 minus x. That's that triangle over there. So that's going to form the base of our solid. Okay, but what does our solid look like in 3D if the cross sections are squares? Well, here's a little image to help us understand. So this three-dimensional diagram is kind of like this two-dimensional diagram. It's got that same x and y axes, but now instead of looking at the xy plane head-on like we did before, we're looking at the xy plane as being kind of like a horizontal plane, and the cross-sections are jumping out up from that plane. So how do we find the volume of this region? Well, we just have to integrate the areas of the cross-sections. The volume is equal to the integral of the areas of those cross sections, those squares. Okay, so this is a step in the right direction. We know that to find the volume, we have to sum up all those areas of the square cross sections, and we do that with an integral. But how do we compute this integral? We need to write our integral in terms of a variable in order to compute it. Why don't we write it in terms of the variable x? So we'll need to find the area of a square cross section as a function of x. Then we'll take that integral dx, and what will the bounds be on that integral? Well, the region ranges from x equals 0 here to x equals 1, so bounds will be from 0 to 1. Okay, so how do we find that area of a square cross-section in terms of x? Well, first of all, let's just think about what we know from geometry. We know that the area of a square is going to be the length of a side, just call that L squared. So if we can find the length of a side of the square in terms of x, then we're good. Okay, so how do we find the length of a side of the square? Well, think about in this diagram, the cross sections have sides that lie in the xy plane, and those sides just range from the x-axis up to the hypotenuse of that right triangle. So if we think about what this looks like in the straight-on 2D plane, then we can draw a side ranging from the x-axis up to the hypotenuse of that right triangle. Why don't we go ahead and draw it right here? So this could be a side of a square. So that could be our function L of x. And we see that that function L of x, well, that just gives us the y-coordinate of this hypotenuse. And the y-coordinates of the hypotenuse are just given by this function y equals 1 minus x. So that means L of x is just equal to 1 minus x. So let's go ahead and make that substitution. L of x is just 1 minus x. And we have to square that. Alright, so now we're in a good position to compute this integral. We can go ahead and substitute in 1 minus x squared for the area of the square inside of the integral. So it'll become integral from 0 to 1. Area of square becomes 1 minus x squared, then dx, and now we just have to compute this. So let's go ahead and compute that. That's the integral of 0 to 1. Let's go ahead and multiply out this inside. We just get 1 minus 2x plus x squared. And that's all dx. Now we can anti-differentiate using the power rule for integrals. So that becomes 1 goes to x, and then minus 2x just goes to minus x squared, and then plus x squared goes to plus a third x cubed. Alright, now we just have to evaluate at our bounds 0 and 1. So evaluating at the bound 1, we have 1 minus 1 squared plus a third times 1 cubed, and then evaluating at 0, well, 0, 0, 0, everything goes to 0, so just minus 0, so we can totally forget about that part and just focus on this part here. So what does this come out to? Well, that's 1 minus 1 squared is just 1, and then plus a third times 1 cubed is just 1, times a third is just a third. So 1 minus 1 plus a third, 1 minus 1 cancels out, and we just have a third. So there we go. The volume of that solid there is a third. Alright, here's another example. compute the volume of the solid which has a triangular base bound by x equals 3, y equals -3, and y equals x minus 2, and whose cross-sections are semicircles. We've got a graph here which shows us the base consists of x equals 3, y equals -3, and y equals x minus 2. Those are the bounds, so we're looking at the region inside, which forms a right triangle here that's shaded in. And we want to compute the volume of the solid whose cross-sections are semicircles. These cross-sections run perpendicular to the x-axis, so one of the cross-sections might look something like this. This will be a side of a semicircle, and the semicircle will pop out like this. Okay, so like before, we know that the volume is going to be obtained by summing up the areas of all those semicircle cross-sections. So we'll have volume equals integral of area of a semicircle, and we need to express this integral in terms of a variable so that we can actually solve it. How about we express it in terms of x? So we'll write area of the semicircle in terms of x. We'll figure out that in a little bit. Let's just complete the integral. It'll be dx, and what are our bounds for x? Well, x ranges from right here, that's at -1, to over here, which is at x equals 3. Now, what is the area of a semicircle in terms of x? Let's write that down. A semicircle as a function of x, what does that equal? Well, we know from geometry that we can simplify the situation a bit. What's the area of a semicircle? Well, that's just a half the area of a circle, and the area of a circle is given by pi times radius squared. So pi, we'll write this, we need to find the radius as a function of x, and then stick it in this formula, and then we'll be able to compute the integral. Okay, so how do we find the radius as a function of x? Well, why don't we draw that in on our diagram here? So the radius of that bit of cross-section that we've drawn here, that would just be half of the length here. So that's r of x. And how do we find that half of the length? Well, we can find the full length and then just divide it by 2, take half of that. So why don't we write that radius of x is equal to a half of the full length down here. And what is the full length? Well, we can just subtract the top y minus the bottom y. So a half of y equals x minus 2, take x minus 2, and then subtract the bottom, so minus -3. Alright, inside the parentheses we've got x minus 2, then plus 3, so x plus 1, and then just that over 2. Okay, great, so now we know the radius as a function of x. We can just stick that in for the radius here, which gives us the area of a semicircle as a function of x, and then we'll put the area of the semicircle into the integral, and then we'll be good to go. So let's go ahead and solve that integral up here then. So volume equals integral from -1 to 3, area of semicircle, let's start writing that down, a half pi, and then r squared. We stick in the expression that we found for the radius, which was just x plus 1 over 2, so x plus 1 over 2 squared dx. And now we just have to solve this integral. Alright, so let's go ahead and solve it. First, let's just simplify as much as we can. So let's simplify the inside. It'll still be integral from -1 to 3. We'll have a pi over 2 in front, just combining that, a half times pi. And then let's square this expression here. So times, on the top we get x plus 1 squared, and then on the bottom we get 2 squared, which is just 4. So that integral of that dx. Now let's simplify even further. Let's take this pi over 2 times a fourth and move it outside. So we'll get pi over 8 on the outside. Pi over 8 times the integral from -1 to 3 of x plus 1 squared. Great. Now let's go ahead and expand out that inside. So get pi over 8 times integral from -1 to 3 of x squared plus 2x plus 1, that all dx, and now we can actually take the antiderivative. Great, so pi over 8 times, what's this antiderivative? Well, antiderivative of x squared is just a third times x cubed, antiderivative of 2x is just x squared, and then antiderivative of 1 is just x. Alright, great. So now we just have to evaluate that at the bounds -1 and 3. So we'll have pi over 8, and then evaluating at the first bound at 3, the upper bound, we've got 1/3 times 3 cubed, then plus 3 squared, then plus 3, and then minus at the lower bound, so that's pi over 8, stick in -1 for x, so 1/3 times -1 cubed plus -1 squared plus -1. Alright, so this is pi over 8. Let's try to simplify the inside. So a third of 3 cubed, well 3 cubed is 27, and then a third of that is just 9. So 9, then plus 3 squared is 9, then plus 3. Alright, then minus pi over 8 times 1/3 times -1 cubed. Well, -1 cubed is just still -1, and then times a third, -1/3. Then plus -1 squared, -1 squared is just 1, so plus 1, and then plus -1, so minus 1, and we see that we can cancel out this plus 1 and minus 1 here. We're starting to run out of room, so let's take this and move it up here. It's just a little bit more simplifying that we have to do. So this is pi over 8 times 9 plus 9 plus 3. Well, 9 plus 9 is 18, then plus 3 is 21. Okay, and then minus pi over 8 times -1/3, and then the rest went away, so just pi over 8 times -1/3. So this becomes 21 pi over 8, then plus, because negatives cancel, pi over 24. Now we want to add these fractions, so let's have them get the same denominator. Multiply this left one by 3 over 3. Alright, so that'll give us 63 pi over 24 plus pi over 24, and that comes out to 64 pi over 24. And we can reduce that, divide top and bottom by 2, that goes to 32 pi over 12. Both of these are divisible by 4, so divide by 4. 32 divided by 4 is just 8, so 8 pi, and then bottom 12 divided by 4 is 3. So 8 pi over 3. That's our final result. That's the volume of that solid whose base is here and whose cross sections are semicircles. In this video, we focused on finding the volume of solids which have triangular bases. However, in the future, we'll also learn how to find the volume of solids which have bases in other shapes, such as circles or even arbitrary curves.